Okay, this is the second part of Unit 8, which is all about a law called Coulomb's law. Okay, Coulomb's law is a mathematical relationship dealing with the electric force between two objects. So the force due to the electric charges between two objects. And it's the force, like Newton's third law of motion says, the force on one object is going to be equal and opposite to the force on the other object. So the equation is K Q1 Q2 over R squared. Q's are your charge values. R is the distance between them squared. K is something called Coulomb's constant, called the electrostatic constant, which is 8.99 times 10 to the 9th newtons times meters squared per Coulomb squared. And one thing to notice about this, just like you can think about with gravitational forces before, the relationship between the force and the distance is an inverse square relationship. So if you quadruple your radius, the distance between your charge, the centers of your charges, if you quadruple that, your force between them is 1/16 as much as it was before. All right, so Coulomb's law describes the force between two charged objects. So these two like charged objects are going to have a repulsive force between them that is going to get progressively smaller as they get farther apart. All right. And it looks much like Newton's law of gravity. And the direction of the force is determined by the second part of Coulomb's law, with the positives and negatives. If they're like charges, they repel. If they're opposite charges, they attract. So if you have a positive force, that is a repulsive force. A negative force is an attractive force. So Coulomb's law is a force law, and forces are vectors. So the electron forces can be superimposed. So we can say the net force on a charge is equal to the force on it from all other objects. All right. So we can use this to find the force between different charges in an electric field area where electric charges are. So you can draw vectors on an x and y coordinate system. So example here. So we're going to look at the charge acting on the force pulling on this particular charge in the middle. So the first one shows opposite charges, so they're repulsive. And then this one, all the charges in B here, all the electric forces are pointing towards the negative charge. The two positive charges repel each other, and the positive and negative charge are attracting, so all the forces are going towards the right in this one. Okay. So we can add up all these force vectors over here. On the top one, the net force on this one is 0. Because we have equal charge values, which means we have equal and opposite forces, so the net charge on A is 0. On B, we have to add up all these forces. Add up F on 1 on 3. So both these forces here, 1 on 3 and 2 on 3, get our net force in the right, going to the right. Which is Coulomb's constant times the one object has a charge of 10 newtons, the other object has a charge of 1 newton, over the distance between them of 0.10 or 0.01 meters squared. So our equal forces are the total, both of these. Since these two forces are equal, F1 on 3 and F2 on 3, those are equal, everything's going to the right, and you have a net charge to the right. So with this one, this I want you to solve on your own. Go back and look at how they solved this. and find the magnitude and direction of the electric force. So point A has a charge of 1 Newton Coulomb and point B has a charge of 4 Newton Coulomb. They are separated by a meter. So hopefully you can see that the directions between them, they're opposite charges, so they're going to be an attractive force. The force is going to be a negative force. And you have to convert from nanocoulombs to coulombs. Okay. So here's another sample problem here. Small plastic sphere is charged to 10 nanocoulombs. It is held a centimeter above a small glass bead at a rest table on the table. So this is what we have. The bead has a mass of 15 milligrams and a charge of 10 nanocoulombs. Will the glass bead leap up to the plastic sphere? So when we look at the vector diagram here, we have some forces acting on the glass bead. Gravitational force, normal force, and the force between them. So we can say that. So we have the plastic sphere is Q1, 10 nanocoulombs. The glass bead has a charge of positive 10 nanocoulombs. If the glass bead will rise if F1 on 2 is greater than the weight. If it's less than the weight, the bead will remain at rest. So if F1 on 2 is greater than the weight, it's going to rise. If F1 on 2 is less than the weight, it will not do anything. It will stay there. Because the net force will be going downward. So using the values provided, we can find that the F1 on 2 is Coulomb's constant times negative 10 nanocoulombs times 10 nanocoulombs divided by r squared, 1 centimeter squared, gets us 9 times 10 to the negative third newtons. The weight of this thing is the weight of the mass of the glass bead times acceleration due to gravity, which is less than the force, so the bead will indeed rise. That means the electric force between these two things is stronger than the force of gravity acting on the glass. It will rise. It has a net upward force. Okay, so two honeybees each acquire a charge as they fly back to their hive. As they approach the hive, they are a centimeter apart. What's the magnitude of the repulsive force between the two bees? How does this force compare to their weight? So again, remember this happened. This can actually happen when like a bee rubs over something when they're acquiring nectar for honey. Okay, so if we look at the answer here, the weight of each bee is its mass times gravity, which is 1 times 10 to the negative third newtons. So the repulsive force is Coulomb's constant times Q1 times Q2 divided by 0.01 squared. So this is your radius squared. So Q1 and Q2 are 23 picocoulombs, really, really small coulombs, not much. And K is 9 times 10 to the 9th. So the magnitude of the electric force between them is 1 times 10 to the negative third squared times 9 times 10 to the 9th divided by 0.01 squared, which is 4.8 times 10 to the negative 8th newtons, which is much less than the force of gravity in this particular case, so that charge won't do much to them. So when we're looking at Coulomb's law, it's all about looking at the formula here and seeing what happens between two objects. Okay, so we have this quick little simulation here. So if I put my two charges equal, you should be able to figure out the force between. Now, even if I decrease the charge on one, notice the forces remain consistent. And now all of a sudden, if I do this, now I make them the same sign, now the forces are repulsive. But you can, all this is simply using the Coulomb's law equation with a little simulation here. Right? So again, make sure you ask questions on the bottom. And we'll talk about this more in class. And we'll talk to you soon. Bye-bye.